Thank you very much for your introduction. So this talk is very different from the previous one, so we don't go through the numerics really. So this is a joint effort between STFC, where I work, and University of Sheffield. So the three first people, Wei, Bo, and Greg, have been working on that project for runs modeling, and Junie He has been developing, running the simulation for the reference data. And the ideas behind the benchmark is Shisheng He. And Stefano and I have been advising on the project. So before talking about the benchmark itself, so we would like to give kind of justification why we think that nuclear could be useful, and what it represents in the UK for the energy mix. So there are only 2 points on these plots, basically. So, but the nuclear is pretty much constant, but you can see that wind and solar energy actually they increase by at least 10%. They increased by at least 10% in 1 year, while gas was reducing by proportionally as well, about 10%, given that all the other source of energy were kind of constant. So the coal has to go by 2050 in the UK. And so we think that nuclear can be useful when the renewable are not effective, like when solar or where basically there's no sun or there's no wind. So this is just to set the scene a bit. And now going for a different type of nuclear reactors, they use a device called this reactor vessel auxiliary cooling system that is used either in normal operation or also in case of accident, basically. And it's used to remove the decay heat of the reactor vessel. So this is the reactor, really, who can be very, very hot. And this device is just all the way around it. So you've got an inlet part and the outlet part, and it goes around the baffle to be sure that it is going to cool down the outlet of the vessel itself. So it's used for all the reactors which have been designed with these passive safety features. But from the literature, it basically mainly fits reactors for the next generation, which are Gen 4 reactors, knowing that in the UK, they don't have Gen 3 reactors yet, so that should be in production in a couple of years. And they are decommissioning the Gen 2 ones. So that's basically kind of working for the future. And the type of coolant they use for this device is air, knowing that it can be applied to different type of reactors, which coolant is either helium, liquid sodium, or liquid lead. So now some background on the benchmark itself. So we think that this exercise is quite important, because what we're after is that we're after looking at kind of lower Rance models. So it's first order Rance models, usually with 2 equations. So based on K epsilon, basically. So, and we think that we would be good to have a model who can predict quickly and give some answer, for instance, in case of accident, which is going to correspond to the natural convection here, knowing that this device, this RVCIS, is normally operates with a mixed convection. So we've got 3 scenarios that we have identified. So natural convection, mixed convection, and also forced convection. But forced convection is more to assess the performance of the turbulence model, rather than being a scenario that could happen during production. Sorry. Did I pass one? No. sorry. So basically, the aim of these studies is to identify the different CFD packages. So here we focus only on one. But when this benchmark has been given, there were 4 or 5 different groups having 4 or 5 different software. And of course, the turbulence models, if they are the same, they might be implemented in a different way. So that's why that was also an idea to assess the expertise and the knowledge of the people running these simulations. But also there were comparison between mesh strategies and the lower turbulence models which were used. And the idea is to investigate the impact of buoyancy on turbulence and heat transfer, knowing that we're going to be in a case where when we have conjugated transfer, we need to simulate the flow in the fluid and the flow in the solid. So if we look at this sketch, so in case of mixed convection, so we got an inlet here. So it goes down mainly through gravity, and then it goes up because of temperature difference and a bit between the two walls. And this thin bit is actually the buffer, which is going to be meshed as a solid in some cases for natural convection, or in the other case, when we don't do conjugated transfer, we actually use boundary condition on this bit. So we assume for our case that, we use a symmetry or axisymmetry, and the presentation of the work is 2D, while the references are obtained in 3D. So here the configuration. So we solve the Lomax number, the Lomax form of the Navier-Stokes equation. And we need to do that because the thermophysical properties can vary a lot, and they are basically temperature dependent. So for natural convection, we close the domain, and the inner wall we correspond actually to the outer wall of the reactor is very, very hot, while the outer wall is basically 300 K kind of room temperature. And so there's a difference of 400 kelvins here. So the heat transfer coefficient are all the same for all the simulations. So we close, in this case, the cavity for natural convection and for mix and force correction. So we've got an inlet there, and we use a fully developed turbulent flow at a Reynolds number of 180, and we impose a temperature. So as said before, in this case, we use conjugated transfer, and here we've got boundary condition on the buffer, or here as well. Basically, that's the buffer top. So here the direct numerical simulations which were run, and there are 2 films, one showing the velocity magnitude. And the flow is quite complex, especially for runs models. So you got the inlet here. After that, it goes down the buffer, so it looks like a channel flow. Then there's a lot of mixing here, which is very difficult to predict by the lower order model you are using. And then a recirculation again, and after that, a kind of boundary layer until it becomes like a channel flow. And you can see the thermal boundary layer here. In this case, so the code which was used is NEC 5000. I think we've seen it quite a lot in this conference. So the Y plus is around 0.1 in most of the walls. So that's probably give a T plus of 1. So the thermal boundary layer should be captured properly. So this is a set of equations we are using. So this is actually classical tools that have been used, and there are 300 million elements for this simulation. So this case is 3D, obviously, because it's a DNS. And knowing that we're going to model in 2D, and now we're going to use code Saturn, which is a second order, at best a second order code in space and time. So the boundary conditions are related to what I said before. So we got a fully developed flow profile for mixed convection. The outflow is typical outflow with the pressure being constant and no boundary condition on the other quantities. And so for momentum equation, we use the Dirichlet boundary condition and convective for energy. And for the buffer wall, it depends whether we're using CHT. So we've got an internal coupling for the solid simulation. Otherwise, it's adiabatic. And the other wall is a Dirichlet boundary condition for the momentum and adiabatic for energy. So the scheme is that we want to be sure that we are second order at best. So we use some kind of upwinding in some places that requires some stability, extra stability, and it's first order in space for turbulence on in space for turbulence, and first order in time for because we are running actually we are going steady state simulation, but in NCD mode. So the pressure velocity coupling is simplex, and the meshes are very small when we use wall function. So that's run in a few minutes only on one core, 1 MPI rank. And the other mesh for low Reynolds turbulence model is about 1 million. So it's 96 cores on slow cores basically. And we make sure that the Y plus fits the model range. So Y plus is above 11, is closer to 30 actually, for the high Reynolds numbers, and for the other one is lower than 1. So it's lower than 1, but I mean we don't have much information about T plus, so we might not capture actually the thermal boundary layer. So here is how the coarse and fine mesh look like. So, well, that's a traditional structured grid. So please note that the code is unstructured, but actually supports structured meshes. So we use that code because it's developed by EDF, which is the main electricity provider in France, and this is a dedicated code for a lot of internal flows in nuclear reactors, mainly. So we tested all these RANS models, and the one highlighted in orange is the one we actually focused on here. So the important thing is that there are two high Reynolds number models. They are all based on K epsilon. Here is corrected with a K omega close to the wall. And you've got two scale velocity log-low when you are beyond Y plus of 30. That's for momentum, and a Van Driest approach. So basically some damping it's not really a well function, it's some damping actually. So, and there are three low order Reynolds number models we've been testing as well. So these models are actually very old. So the youngest one, which is from this millennium, is this one. So all the others are way okay. So I was going to skip this bit. So the investigation we look at is that, so this is a complexity of the flow. So we've got several lines we look at. So, and so we've got this kind of heat map. Is that basically when you look at this plot, is that the lighter the color, the better the model is. So we tested natural convection with conjugated transfer. So and basically, so we computed all this and we plotted in different line 2, 6, and 10, which correspond to different type of flow. And for instance, for here, the one with the lightest, which returns the lightest color, is a Landau-Sharma model. And okay, we would need to zoom a bit on these pictures, but what happens usually is that on this part of the flow, Landau-Sharma is not doing very well, but from the mixing up and this part is actually doing a very, very good job. And this is actually this part we're interested in because this is where the reactor vessel is, and this is where all the heat is. So that was for the velocity. So now for the temperature, we got, I mean, the very, very similar results. It's again the Landau-Sharma model who gives the best results. And here we computed the temperature in the fluid as well. And it's again the green part, we actually recover the temperature in the solid. So now, if we move to mixed convection, so that's without conjugated transfer. So this time we've got adiabatic boundary condition on the baffle. So it's a little bit more difficult to to get decent results in this mixing bit. So I will say that corresponds to line 2. So basically, the models are all over the place compared to the DNS, and the DNS might not even be fully converged actually. So this test case is much more difficult for at least to pick up the velocity. So the only thing we can say is the old Reynolds high Reynolds number with Wolf function seems to give the best results on this side, and on the other side is Landau-Sharma again. So I mean, we don't have a blending between these two models anyway. So now for the flux temperature, the results are not too bad, and it's again the high Reynolds number, which seems to give the best results. And okay, and in the solid, for the solid temperature, that's Landau-Sharma, which is the closest. And I said, I think there's I mean the DNS data might not be converged. I see it a bit scattered here. So now this is the last test case we've been running. So that's forced convection, and I said doesn't correspond to operation product. I mean real production situation, and so in this case, this was to assess the turbulence models. So again, when we go downwards, is a green line, so which correspond to the high Reynolds number K epsilon, basically, with Wolf function, which is the best. And again, when it goes up, well, after the mixing, it's a Landau-Sharma. So overall, well, I can conclude now actually. So this is roughly the same trend for the temperature and for the solid. So this is without CHG again. But then to conclude, we found that for natural convection is the Landau-Sharma model predicts the best the results. So this natural convection correspond to it could be could happen due to an accident. So it's very good to have identified just one model for that. For mixed convection, and forced convection is a little bit more difficult to pick which model we want. And yes, so that's what I wanted to say. And apart from, we were very surprised that K omega actually didn't give the results we expected, because it's usually the first turbulent model that people pick. So thank you very much.